Thanks, Priya, and thanks for having me. I'm really honored to be here. So I'm a philosopher of science, interested in causation and causal modeling. I work on both sort of fairly concrete issues about the nuts and bolts of causal modeling, but also on sort of much more abstract and high-level issues about sort of the foundations of causal inference and how causation and causal inference sort of fits in a sort of physics-based picture of the world. And so today my talk is going to be much more on the abstract, high-level side. It's going to be sort of fairly disconnected from the sort of day-to-day methodological issues that you might face in science. But essentially what I'm going to focusing on is this phenomenon that has puzzled physicists and philosophers of science for a long time, which is that in some sense it's easier to infer the past than the future. I'm going to try to tell a story as to why that's the case that I think brings out some interesting facts about causal inference and how sort of the physics of our world puts constraints on the kinds of causal inferences we can make about the past or the future. So what do I mean when I say that it's easier to infer the past than the future? I'll tell you in a minute if I can find a way to move my slides. All right. So what do I mean when I say it's easier to infer the past than the future? Well, I can give you a couple of perfectly mundane examples to get to see what I mean. If you want to figure out what the weather was like exactly 10 years ago in New Haven, you can of course consult the weather records, but it's impossible to predict what the weather is going to be like in exactly 10 years. From now, if you see the footprints in your garden, you can figure out, a fox visited last night, but there's no sign in your garden that tells you a fox is going to visit tomorrow night. You can see the dent in the car and figure out there's been a collision recently, but again, no mark on the car that tells you the car's going to be involved in a collision in the future, right? So perfectly mundane examples. Looking at more interesting scientific examples. We have all those sciences of the deep past, like cosmology and geology and evolutionary biology that give us very detailed and reliable accounts of the sometimes very distant past, but we don't have anything like a comprehensive scientific account of the distant future, right? And so that's the sort of phenomenon I'm interested in sort of trying to explain at a very, very general level. And you might think, the explanation for this sort of asymmetry of inference, it's obvious. It has to do with the fact that the future, by definition, hasn't happened yet, right? So it's still open, and that's why we can't know about it. But the past is settled and it's fixed, and that's why we can know about it, right? So there's a couple of issues with that, but perhaps the most obvious one is that we do, of course, make plenty of successful predictions about the future. Again, using perfectly mundane examples to make the point, we can predict when the next solar eclipse is going to be in the US. I can see the smoke rising from my cooking pan and figure out that the fire alarm is going to beep in a few seconds, so on and so on, right? Again, all of this is perfectly obvious. So the contrast here seems to be really that when it comes to making successful predictions, we're sort of restricted to very special contexts, like contexts having to do with isolated systems, like in the solar system example, or with the immediate future, like in my cooking pan example. Or, we can perhaps make predictions about the longer-term future, but they have to be sort of very broad brush, very vague. Like I might predict that, the Russian invasion of Ukraine is going to have drastic consequences on, say, European geopolitics in 10 years, but I might not be able to make any more specific predictions than this. But when we turn to inferences toward the past, there's no such restriction, right? Again, we can make sort of very detailed, very precise inferences about sometimes the very distant past and about systems like the weather or species that are not at all isolated from their environment, and whose dynamics may be, in fact, quite chaotic. Right? And the point is, a sort of blunt distinction between an open future and a fixed past is not going to be able to explain that contrast. Right? So presumably, instead, the answer for why it's easier to infer the past than the future has something to do with the physics of our world, right? It has to have some sort of physical explanation. But there's somewhat of a mystery here because the answer or the explanation, it's not going to come from the fundamental laws of physics, because the fundamental laws of physics are time symmetric. They don't really distinguish between the past and the future. We've known since Newton that there's no real intrinsic direction of determination in the laws of physics. Earlier states of the world determine later states just as much as later states determine earlier states, right? So in relativity theory, for example, what's going to happen at time zero here, it's going to be fixed by the cross-section in the backward light cone, but it's also going to be fixed by the cross-section in the future light cone, right? So there's no asymmetry here. And so there's this so that means, from the perspective of the laws of physics, there's no real reason to expect the future to be harder to predict than the past. So there's this mystery that has puzzled physicists and philosophers of science for a while. And some of the people in this room have worked on this as well. Here's some of the relevant literature. The starting point of all of this was Hans Reichenbach's work in the direction of time. Now, one idea you find in Reichenbach is that this asymmetry has to do with entropy increase and with the second law of thermodynamics. So there's a very sort of influential tradition of exploring that line of thought. There's also an idea you find in Reichenbach that the asymmetry of inference has something to do with causation and with the distinction between causes and effects, and with what Reichenbach called the principle of the common cause. So that's more the line of thought I'm interested in exploring today. And what I'm going to say sort of systematizes some of the things that Reichenbach says in his book, but that I think people haven't really picked up on too much in this literature. And so the big picture is something like this. The kinds of inferences we make toward the past and toward the future, they are and they have to be causal inferences. They have to involve cause and effect reasoning, right? So inferences toward the past, they always, or at least almost always, involve deriving a past cause from a present effect, right? Only a fox could have caused those footprints. Only an organism with this and that feature could have produced the fossil that's in front of me, and so on. And inferences we make toward the future, they involve deriving a future effect from a present cause, right? The smoke rising, that's going to cause the fire alarm to beep. The Russian invasion, that's going to cause this and that consequence 10 years down the line, and so on. It's no surprise, of course, that all the inferences we make toward the past or the future are causal, because to infer an event from another one, there needs to be some kind of correlation between them. And correlation is usually at least going to require some sort of causal connection between those two events. And so the hypothesis here is that maybe there's something about the cause-effect distinction that makes it easier to infer the causes of events than their effects. Maybe there's something about the cause-effect distinction that makes it easier to infer causes from effects than to infer effects from causes. And I apologize for the sort of mismatch in the slide. This wasn't like that on my computer. Of course, to make good on that hypothesis, you're going to need to explain what exactly distinguishes causes from effects, and why that distinction would sort of give rise to this asymmetry. And that question, the distinction between causes and effects, that's also something that has puzzled physicists and philosophers of science for a long time. Again, because the fundamental laws of physics, they're not really causal. They don't really distinguish between past and future. They don't have a direction of determination. So there's sort of a mystery as to how something like a robust cause-effect distinction emerges from physics. And like many people, I think, the answer at the end of the day comes from the work done in the causal modeling tradition, which itself systematizes some ideas of Reichenbach. And the thought here, and I assume this is familiar to everybody, is that the kinds of causal structure we see in our environment, they can be represented in the form of acyclic graphs that represent relationships of direct causation between variables. And the sort of key principle or the key assumption is that there are going to be some principles that relate the causal structure of those systems to their statistical structure. And the most important one is the causal Markov condition that tells you that exogenous variables, sort of initial causal conditions, the causal inputs to your system, they're not going to be correlated with one another. Their values are going to be fixed independently. So in the model over here, S is not going to be correlated with W. But by contrast, endogenous variables, the effects of the system, they can and usually are correlated with each other, at least when they have a common cause. Right? Common causes are going to create correlations between effects. So X and Y, for example, here are going to be correlated because they have a common cause. Right? So the idea is, at a very general level, that's what the cause-effect distinction is about. It's about, causes are the variables that tend to be statistically independent of one another, and therefore are sort of the causal inputs of the system, and the effects are those variables that are correlated with one another. And what I want to try to suggest in the rest of the talk is that it is that asymmetry, the causal Markov, the asymmetry encoded in the causal Markov condition that explains why it's easier to infer causes from effects than vice versa. And the claim a bit more precisely is that the causal Markov condition is going to entail, in a number of circumstances, that the probability of an effect given a single one of its causes is going to be very low, except if you're in a special context where you're dealing with an isolated system, or again, the effect is in the immediate future of the cause or something like that. But by contrast, because the causal Markov condition doesn't require effects to be independent of one another, it allows for correlations between them. It's going to entail that the probability of a cause given its effect can be very high, even if the cause is in the very, very distant past, and even if the system we're dealing with is not isolated at all. I'll give you an example to try to sort of make this a bit more concrete in a second. But one other idea I want to put on the table here is that when you think about causal inferences and inferences to the future or to the past, there's a kind of mystery of how limited beings like us can ever infer anything about the past or the future, because the physics of our world seems to put a lot of obstacles to that. The problem again is, the problem is that the dynamical laws of physics that govern our world, they're global in the sense that they relate global states of the universe. So again, in relativity theory, to figure out what happens at a space-time point, you need information about the entire cross-section of the light cone, either backward or forward. And typically that's going to be an enormous spatial region, right? And of course, we can't observe global states, right? We have to make do with very localized and partial observations. So it's kind of a mystery of how we can use those local observations to ever predict or retrodict what happens at other times, right? Given this sort of drastic underdetermination. And the thought here is going to be that the causal Markov condition, or the causal structure of our world, it removes that obstacle. It makes it possible to make inferences from local events. But it's going to remove that obstacle more towards the past than towards the future, as you might say. There's still going to be an enormous epistemic predicament in trying to figure out what the future is like. Okay. And a remark for the philosophers in the room. I mentioned there's this other line of thought about the asymmetry of inference, that this has to do with entropy increase and so on. The best version we have of this story today is due to David Albert, and you might be wondering what's the relationship here. Maybe I'll say a few words about this at the end if I have the time, but very roughly the idea is the two stories are sort of compatible and complementary, but there are also some important nuances about how central the causal asymmetry is in sort of the picture of the world, and how temporal asymmetries emerge from physics. I'm just going to walk through an example here to sort of try to make good on those various claims I've made here. It's not going to be a very interesting example of historical scientific inference. I'm a philosopher. I use mundane examples because they help make the points more simply. But the idea is, this is an example we can use to think about inferences at other times in general, including the sort of very sophisticated inferences you find in evolutionary biology and geology and so on. So what you have here on the left is the Mayflower departing from Plymouth in England to America in 1620. And here on the right is a random plaque I found on the internet in Harwich in the UK that commemorates the departure of the Mayflower in 1620. I mean, it says a number of things, but one thing it says is that this here happened, right? And obviously there's a causal relationship between those two. So even if you know nothing about the Mayflower or anything, as long as you read English, you can walk by that plaque, read it, and then come to learn that this event happened, right? If you go around reading plaques, you'll get it right most of the time. Plaques are really reliable, right? So it's very, very easy to make that inference here from the effect to the cause. But of course, nobody who had witnessed this here would have been able to predict the existence of the plague 4 centuries later, right? There would have been, if you had predicted that, you would have been insane. And so that's a case where, if you want to put it in terms of probabilities, the probability of the effect given the cause is very high, but the probability of the effect given the cause, the probability of the effect given the cause is very low, but the probability of the cause given the effect is very high, right? So again, I want to think about it, what explains this at a very general abstract level? What explains this asymmetry here? And looking first at sort of the cause to effect direction, right? It's obvious why nobody would have predicted the existence of the plague 4 centuries later if they had witnessed the departure of the ship, right? Because, the departure of the ship obviously was not causally sufficient for the existence of the plague. A staggeringly large number of other factors had to be in place in 1620 to later lead to that event, right? So that includes all the factors that would later make the Mayflower or its departure a significant event in world history. So, facts about the weather that would ensure that the ship doesn't sink and gets forgotten. Facts about the Wampanoag people who would provide assistance to the ship's passengers in Massachusetts and so on. And also facts about, facts that would later lead to the emergence of plaque making as an important practice of memorialization in the 19th century and so on and so on. And of course, there's a clear sense in which those factors all lining up in the right way. That was enormously unlikely, right? And that's why, just witnessing again that event here would not have let you predict this. And I think this is a more, there's a general story here as to why it's so hard to predict events in the future, especially the distant future, from their causes. If you observe an event C here that's later going to produce an event E, whether E is going to happen, that's also going to depend on many other causal factors, right? And if the event E is it's in the distant future, often you're going to need an enormous amount of such factors, and the probability that they're going to line up in the right way is going to be very low. And that's why observing the cause alone, that's not going to tell you that the effect happened, right? The probability of that is going to be be very low. And so one lesson here is that I mentioned this epistemic predicament that we face, that we can only make local observations, but we live in a world governed by global laws, right? Well, one idea is that at least when it comes to predicting the future, that predicament is very severe, right? The fact that the laws are global means that a local cause is never going to be sufficient for its effect. You're always going to need more factors to entail it. And that means, to make a reliable predictions, you would have to be able to observe all of this. But that's going to be spread over an enormous spatial region. And of course, we can't make observations like that, right? We're limited to observing the things around us. So hopefully, so far, again, this is highly abstract story, but I hope it makes sense, and perhaps it strikes you as perfectly trivial, even, hopefully. Where things get interesting is if you think about what happens in the reverse direction when you go from effect to cause. So now when you're reading the plaque and learning about this event here, because I said, that's here we want to say intuitively the probability of the cause given the effect. Here it's very high, right? But it's sort of a mystery how that can be the case, because the global character of the physical laws that, makes it impossible to predict the future, it's also present towards the past. The global character of laws, it's a time-symmetric feature of the laws. What that means is that just like a local cause is never sufficient for a later effect given the laws, likewise, a local event is never sufficient for its past cause, given the laws. The laws are always going to tell you, whether the cause really happened depends not only on that local event, but on what happens in an enormous spatial region. Again, to figure out what happens here on the basis of there, you need, the laws need information about everything that happens here. Right? To make this a bit more concrete, one way to see this, or to see that, in the case of our little plague here, it's not sufficient given the laws for this to happen, or to have happened, is to think about all the other effects of the departure of the Mayflower that are sort of scattered in the macro-state of the world right now. So this includes things like, statements in encyclopedias, monuments to the Mayflower, memories in the brains of historians and school children, and so on, right? And imagine for a second that all those other records, say nothing about the Mayflower, or say that it departed at some other date or something, right? Well, presumably then the laws would say, the plague is most likely the result of a mistake or a prank or something like that, right? Now the laws would say, this past cause never really happened. So that's one way to see that, whether this thing really happens. As far as the laws are concerned, it depends on what happens globally over here. But again, just seeing this here is enough to make the inference. So that's sort of a mystery again. And the thought is, this is again a general feature. There's nothing specific about my example. Whenever you see a local effect here, and you're trying to predict a past cause C of it, well, whether C really happened, as far as the physical laws are concerned, that's also going to depend on all the other effects of C. And if all those other effects are absent, or if they say something different, then the laws are going to tell you C most likely didn't happen. Right? So the upshot here is that we have this sort of deep symmetry at the physical levels between cause to effect inference and effect to cause inference. Right? And the question is, what breaks the symmetry? What makes it so that here the probability of the effect given the cause is very low, but here the probability of the cause given the effect, it can be very, very high. But I think if you think about it in terms of causal modeling and the asymmetry between causes and effects that's encapsulated in the causal Markov condition, then the answer becomes clear. the causal Markov condition, it's going to tell you, looking first at the sort of cause to effect case, right? Those variables here, C and the other causes of E, they're exogenous variables, right? So the causal Markov condition tells you there's not going to be any correlation between C and the other causes of the effect you're trying to predict. And that's why the probability of E given that effect, that cause alone, has to be very low. One way to say this is suppose that C was correlated with all those other conditions, x1, x2, and so on. Then the simple occurrence of C would make those conditions very likely, and therefore the occurrence of E also very likely as well, right? So here, just observing C would provide a lot of information about what's going to happen in the future. But it's precisely the sort of correlation between exogenous variables that's forbidden by the causal Markov condition. In the case of the Mayflower, the causal Markov condition says you're not going to find a correlation between, say, the departure of a ship from a harbor and all the other conditions required to make that departure memorable for centuries later. Right? And that's why just observing the departure of the ship doesn't make the effect likely at all. And the reason that this doesn't apply in reverse is that here now we are dealing with effects of a common cause, right? The effect you're observing and all the other effects of C, they're effect of a common cause. And here the causal Markov condition says, those things can and generally will be correlated with one another. And that means the probability of C given E alone, again, can be very high. All that this requires is that there be a strong correlation between E and the other effects of C. That's all that's required for this thing over here to make that thing very likely. So if you think of it in terms of my example, again, plagues generally make the events they report very likely, right? Plagues are reliable in general. If you go around reading plagues, you're going to get it right most of the time. How can that be given that the events they report, as far as the laws are concerned, also depend on many other things in the macro state of the world? Well, the answer is that the content of those plagues is strongly correlated with other records of those past events, with memories in the brains of historians, monuments, what encyclopedias say, and so on. Right? So that's why you don't need to consult the encyclopedias or ask the historian and so on. Right? Just reading the plague is enough. Okay, so the upshot here is that if that's right, it's really the causal Markov condition that explains why we can infer so much about the past, but little about the future. And again, to repeat this one more time, the background here is that we face this problem that the physical laws are global, but we can only make local observations. So there's this mystery as to how we can ever infer anything from those local observations. And the thought is the distinction between causes and effects explains why that predicament is really severe when we try to infer the future, but it's not so severe when we try to infer the past. And the idea is, if you make a local observation, if you see a local event over here, it's not going to be correlated with all the other causes of the effects it's going to produce in the future. So the observation by itself doesn't tell you much about the future. But the local event you observe, it's going to be correlated with all the other effects of its past causes. And that's why your local observation alone can give you a lot of information about the past. I'm not sure how much time I have left, Priya. Do you know when I started?
4 minutes.
4 minutes?
If you want Q&A.
Yeah. Okay. I'll just. One thing I like about the story I've just told is it explains why we can sometimes predict the future. The special context in which we can predict the future, these are contexts where one of the sort of principles I've appealed to in explaining why predicting the future is hard. One of those principles is not going to be it's not going to hold. So when you're dealing with isolated systems, for example, here you're dealing with a system where its future state, is determined by only a small number of variables, right? And the probability that sort of outside circumstances are going to disrupt the system is just very, very low, right? So just making a few local observations about the system is going to be able to predict what's going to happen in the future. But of course, our lives and economies and political systems, the things we're interested in predicting, they're not isolated systems, right? What happens in their future, it always lies at the intersection of multiple independent causal lines, and that's why we can't really predict about them. Immediate future, the story, like in my cooking pan example, right, where I can predict the fire alarm is going to beep in a few seconds. The idea here is, if the effect is really in the near future, there's not much room for other conditions to make a difference. So here, local observation is going to be enough to predict what's going to happen fairly soon. And then broad brush predictions, I know that the Russian invasion is going to have some consequences in the future. I don't know what they are. Well, the thought here is, if you predict a very generic, unspecific effect, the sort of outside conditions that are required for that effect to happen, they're also going to be very generic, and you can sort of safely assume they're in place. So here, you can predict what might happen in the sort of distant future, as long as you remain very vague and very, very unspecific. Couple of questions. What about memories? I haven't really talked about memories as another way to know about the past that we can't apply to the future. I have things to say about this, but won't say them today. There's, skipping the second point here, there's also a question about, if you think about it in terms of physics here, this asymmetry that you find in the causal Markov condition, where does it come from? Well, the thought is it's going to come at the end of the day from certain facts about the initial state of the universe, maybe some sort of initial randomness condition, something like that. So that's how, at the end of the day, you're going to explain why, how time-symmetric physics gives rise to this sort of time asymmetry of knowledge and of inference. Maybe I'll stop here. I'll just leave summary of some of the main points, and there's a paper. If you're interested in looking at it, there's a link over here. So thank you.
Thanks so much, Thomas. Questions?
Yeah, so I'm a little puzzled whenever I hear this kind of thing, because the examples seem to be kind of cherry-picked, and I can cherry-pick them the other direction. Of course, you've got systems, to make any predictions, they have to be pretty isolated, because if stuff's going to come from the outside. Okay, so let's have an isolated system. It could have a chaotic dynamics, then I'm going to have trouble predicting it. It could have a dissipative dynamics, then I'm going to have really good chance I'll predict well and I'll retrodict badly, right? I have a room and I say, all right, it's isolated, it's been isolated for 5 minutes, it's going to be isolated for 5 minutes. There's a little ball sitting on the carpet. And I say, in 5 minutes, that ball's going to be sitting there, right on that carpet. What was it doing 3 minutes ago? Who knows? Could have been rolling in, right? Because of friction, it's going to dissipate. So I can predict well, I can retrodict badly. I see the rain outside and I say, well, I can now make a pretty good prediction that it will say rain in the papers tomorrow. That means from the papers tomorrow, I can make a good retrodiction that it did rain today. From seeing the rain today, I can't retrodict what the paper said yesterday. I mean, it seems to me there's no real pattern here at all. So I'm not really sure what even the datum is that we're supposed to be explaining, because you can pick examples that go this way and I can pick other examples that go the other way. And it has to do with chaotics, it has to do with dissipation. There are all kinds of how stable things are. I see a plaque. What should I infer about what happened? Well, if I'm in 1984, I have to know a whole lot about, is the Ministry of Truth controlling what's on plaques? Maybe I can infer from the plaque that nothing like that. I mean, maybe I can't infer anything. So it seems to me the whole situation is just, kind of much more messy than this suggests.
Yeah, I mean, I agree with a lot of what you said. And I think, if you want to, I still think there is some sort of difference. It's very subtle how to sort of exactly express it. The best I can do is have this claim about, there's a sense in which the context that where prediction is possible, there's a sense in which they're special, or at least, we can sort of list them. It's about isolated systems or the immediate future and so on. But at least when it comes to inferences towards the past, there are certain limitations that don't hold, right? It doesn't have to be about the immediate past. It doesn't have to be an isolated system, and so on. And the thought is, the story here is supposed to explain why that's the case. So you can think of the story as saying, there is one obstacle to predicting the future. It has to do with the globality of the laws of physics. Why isn't that obstacle an obstacle to inferring the past? Well, the answer is, something about causation. But of course, that doesn't mean we can infer, we can infer everything about the past. We can't, retrodict the trajectory of the ball. There's going to be plenty of situations where there's just limits to what we can retrodict. What's going to be the explanation for that? Well, I don't think there's going to be sort of a general physical explanation. It's at this point, it's going to be case by case. Right. In the case of plagues, has to do with, the sort of social practices we have and why there's no Ministry of Truth, so on, right? In the case of footprints, it's going to be something about, thermodynamics and human anatomy and so on. So there's going to be lots of little local stories, but if there is something global to say, I think that's something like what I said.
I may ask,
Sure.
take the prerogative to ask the next question. So I'm slightly confused, so I want a clarification.
Sure.
So is one of the issues that predicting the future state is sort of handicapped by the lack of information? It's not about the laws, but the lack of information of the full list of relevant causes, right? So it's incomplete information about causes that may become relevant in the future, which we cannot enumerate at the present time with local observations.
Absolutely. Yeah.
Okay.
Yeah. But the thought is, if you look at the physics, you can get in a mood where that also applies towards the past. And the information I have, it's also in a sense very incomplete to retrodict the past, because the laws of physics tell me it also depends on what happens in this enormous region.
I mean, this is, of course, we're speaking about everything in terms of deterministic.
Yeah, I mean, yeah.
Wading into probabilistic domains.
Right, of course, yeah.
Thank you. Very inspiring. And my question relates to the previous questions. The first one is the way that you've been using laws and global laws, for me, seems to, and maybe you can confirm this, that you have a very reductionist logic, so that the Mayflower as a phenomenon is a set of laws, or is due to a set of laws of physics, which for me, maybe, if that's correct, I'm curious to know if that's an explicit assumption for you. And the other one, which I'm interested in, is about the plaque, and why is the plaque something that we should infer the existence of the Mayflower from? Because if I understand your story correctly, that what is happening in this asymmetry is that the effects are correlated. And because of this correlation, we have this asymmetry. And the causes, they're not correlated. So that's why it's harder to go to the future than go to the past. So then why does a single plaque have the authority or the capability of showing you that this Mayflower should exist? If you're saying that, why is it not a set of effects that make that we can go back to the past easier than that we can go to the future. So why is it not something in the plaque that makes that there was already a set of correlations happening? Why the thing that you said about some social phenomena that this plaque is made in certain conditions, or the fact that if we want to actually understand the Mayflower and that we're not in some Disneyland plaque that says something about the existence of Captain Hook and his ship, and that we need these type of correlations to actually do that.
Yeah, I forgot the first question.
It was about your logic and your reductionism.
I mean, all of this is, there are all sorts of reductionistic assumptions in place here. There are sort of, I guess, common ground in that debate. So, the Mayflower, that's a physical system. It's, at the end of the day, governed, entirely and ultimately by the physical laws. And so there's a mystery as to, explaining how, in terms of the laws of physics, we can make certain inferences about the system, but not others. Very large-scale assumptions in place here. The second one, not sure what to say here. One thing, this is a specific example, and of course there's going to be very specific things to say about why plagues are reliable and so on. But the idea is, the point here is to try to tell a much more abstract and general story, and then, to put it in those abstract terms, the idea is, we find very strong correlations between things in the present and things in the past. We find few correlations between things in the present and things in the future. Qualify that in all sorts of ways and so on. But, and yet, it's, the physics of our world, it seems to prevent those correlations anyway, in whatever direction. And as far as, it's the causal structure of the world that explains the solution. Then after that, if you want to explain, why are plagues specifically very strongly correlated with the events they report? Well, again, it's going to be a local story about, human practices and, why, the people who commission the plagues, they have an interest in, having reliable ones and so on. But the point is, to have this sort of much more abstract, much more general story on the table.
Thanks so much for your talk. So I'm totally on board with understanding the causal asymmetry in terms of this probabilistic asymmetry. And I was curious whether you see as part of your project as trying to say something about why those asymmetries get manifested given the way the universe is. So even given everything you've said, if you did not have independent causes, then it would trivially be true but unhelpful. Causal marker would apply. You couldn't use it for anything. And it seems to me there are sort of ongoing debates about this. So I take the story as someone like Dan Hausman says. He appeals basically to the same asymmetry, and he would say that there's no causation in closed deterministic systems. So it's only when we coarse grain and consider sort of open subsystems. And it seemed to me the orientation of your talk went in that direction. Matthias Frisch disagrees. So I'm curious whether this is part of your project to then say something about that.
Good. Thanks. I'm more on the side of the causal asymmetry. It sort of emerges when you're coarse graining the system, and you get probabilities and so on. This is as you mentioned, this is something on which people have had a lot to say, and I don't have much more to add to this. This is sort of the background. You're right, but I think if you think about the causal asymmetry in totally different terms, as these sort of fundamental arrows there is in the world, right? Where, perhaps people who have sort of more robust metaphysics are inclined to think of it that way. You can also tell that story, I think,
Last question. Okay, we have two. Okay. Peter and then Stein.
So I wonder to what extent, really reflecting on whatever.
Sorry, you have to.
I was pressing it, and I wasn't.
Yeah, you don't have to.
Only press it once. Right. Excuse me, I haven't gathered that obviously. So it feels as if the history is very protected in the case of the Mayflower. It really takes an effort of will over centuries for the plaque to exist. And if something is forgotten, then refinding it can be a huge effort. And if there's an effort of will is imposed to deliberately forget, so a criminal wants an act not to be remembered, then the will to forget it becomes a very serious part of whether it is remembered, whether there is a commemoration. So how would you see willpower, just the will, the human will, figuring into this?
That's interesting. Yeah. You're absolutely right here. That in this example, I mean, there's a lot to say about sort of human practices of memorializing certain events and not others, and I don't have anything sort of insightful to say about this. The idea is, at a certain level, the Mayflower thing, you could use examples that have nothing to do with human action and human practices to tell the point. I mean, this fossil over there, it's a sign of the existence of this species, millions or billions of years ago. But physics tells me, whether that species really existed. It depends on not only the existence of that fossil, but actually the entire cross-section of the forward light cone, right? And of course, there's perhaps not going to be any other macroscopic signs of the existence of that species. Maybe the fossil is the only macroscopic record we have, but at the microscopic levels, there's still going to be, correlations. Again, the thought is, how is that possible? How is it possible for the fossil to still provide information if that's the case?
Hey, thank you for the great talk. So what I want to ask is that certainly at the Newtonian level, there is time reversal symmetry in the laws. But at the quantum field theory level, would there be, because CPT is preserved, and we know by matter-antimatter symmetry CP is violated, so time reversal wouldn't hold at the quantum field theory level. So maybe that gives a new perspective of how this asymmetry might arise.
Yeah, this is a great question, and I have absolutely nothing to say on it. This is
actually the cosmologist, but also like time. Yeah.
This is this is outside of my area of not complete incompetence, I guess. And I wish somebody who was knowledgeable about those issues, would answer. I guess one thing to say is, the sort of inferences we make, they're based on macroscopic phenomena, and at the macroscopic level, I mean, I assume the dynamics is, it's kind of quasi-deterministic, right? So I'm perhaps skeptical that going to the fundamental levels is going to sort of tell you or provide the answer here, or because again, whatever asymmetry you're going to find, it doesn't really seem to percolate up, I guess. But again, I don't know much about those issues. Yeah.
I mean, I can answer that question. You might worry in quantum theory, if you've got a fundamental collapse theory, a fundamentally indeterministic theory, then you might be able to predict and not retrodict. Okay, but CPT has nothing to do with it, because even if as long as you obey CPT, there's going to be information preservation at the global scale in both directions. That's not going to break that. That'll be perfectly symmetric, right? From perfect information at any time, you can get perfect information at any other time.
Say that information is not preserved in quantum theory.
Yeah, but the time reversal, you said the time reversal is broken. The relevant time reversal isn't. Relevant time reversal is the preservation of information in both directions.
Thanks once again, Thomas.
Thank you.